Okay, guys, so it's recording. Recording, audio's on. All right, so we've completed basically the discussion of transformer models. Kind of a high level, intuitive way of looking at them. So that was the previous two videos that we did from last week and today. In this session, we are going to focus on the coding side. As you know, in previous lectures, we've actually used the pre-trained models as they are. But with transfer learning, what we're kind of interested in doing sometimes, it is fine-tuning. So I'll give you an example of what I mean. So let's say I'm going to go to the whiteboard, right? And let's say that I have the following problem. I'm trying to, a biologist wants me to develop a transformer model that can help him or her to predict things about plants, right? So they have some plants, some fungi or something like that, flower, and they want to be able to say, well, I give you a sentence, some sentence, blah, blah, blah. And by the way, this is related to the genus of this fungi or some other fungi, right? So it's kind of it's a type of a classification problem, if you will, right? I have some sentence here, and I want to predict something about it. So with transformer models, you can do this, right? So transformer models, let's say BERT, right? So we'll start with BERT. Now, in the previous lectures, we talked about the encoder decoder with multi-head attention, but a lot of the work that has been done actually has been just with BERT, and BERT is just an encoder-based model, so it's simpler in the architecture. Okay, so let's say, for instance, that I have this problem. I don't even know how I'm going to address it. I just know that maybe it's a question and answering system that they want. So the person wants to ask a question about a particular fungi or plant, and then the system is going to say, oh yeah, I read this sentence and I think this is a genus fungi, whatever, alpha. I don't know anything about biology, but kind of like that, right? So it's going to infer something. So it's some kind of an inference engine, or it's maybe a question and answering system, or it's maybe like a classification system, right? So how do I approach this problem? Well, I obviously have some data about this. Let's say I collect a lot of data about fungi. But the data that I collected is only like 100,000 sentences related to things about fungi. So what do? I want to build a question and answer system maybe. So I know that transformers can help me with that. Guys, so what do I do? Do I just take a plain vanilla transformer and train it with this data? Or a much better approach is I'm going to take a pre-trained transformer. Jason, do you have a question?
Oh, no, I was just a little late getting back.
Yeah, okay. So, so as I was saying, you don't necessarily need to train with all the data. This is just the data specific to your task. But because this is like question and answering, what you can do is just take a pre-trained model like BERT, right? Or GPT-3 or one of those. And they're already trained in the English language, right? So they've already looked at, very large corpora of data. They've already learned a lot of the things that we discussed. And so we're going to take one of those pre-trained models, and then we're just going to fine tune it with our fungi or biology data or whatever we want to call this. And then hopefully, by doing that, we'll be able to leverage what BERT already knows but also apply it to our specific problem. Okay, do you guys see that? That's the general approach that we want to take here in solving this problem. I don't even know how to solve it perfectly yet, but I know I want to leverage BERT. So then I need to fine tune a BERT model, right? So I'm going to need some data. I'm going to need to set up what is it that I'm trying to do, and then solve. So that's the plan for today's example. So I want to do actually hopefully 2 or 3 examples of fine tuning and how that works. And then I want to assign you a homework. Okay. So before I forget, the homework that I want to assign to you is I want you to write the code for GPT-2. So GPT-2 is not an encoder type transformer like BERT. It is an autoregressive transformer, much like or similar to what I described in the lecture. So it's more similar to the original Vaswani paper, encoder decoder with multi-head attention. Okay, so don't forget, that's what I want your homework to be, is for you to create the code, or I'll give you some code, but for you to finish up the code to build a GPT-2 transformer for language generation. So what that means is you're going to say to the transformer, Ukraine, and now tell me something, and then it's going to start telling a story. Okay, or you're going to tell it fungi, and it's going to start telling you a story. Right? That's called natural language generation. So that's the type of transformer so that will be the homework. But for this, for our very first example, we're actually just going to take a BERT model and fine tune it for a task, a specific task. Does that make sense? Are there any questions I should say before I begin? No questions? All right, then for this, I'm not gonna use a Jupyter notebook. We're just gonna do this in the prompt. I'm using my my computer here. So let me just SSH into it. And then I'll share the screen. So I need to stop sharing that. And I need to share. By the way, all this code is already posted on my GitHub, okay? So you can just get it from there. Can you guys see the terminal?
Yes.
All right, so let me see where I am. Okay. I'm just going to navigate to the teaching. And I'm going to create a directory here called transformer. Course. Okay. All right, so I'm going to navigate in there. Okay, so here we are. Then I'm going to look at the environments. So I'm using PyTorch on this one. Although, yeah. Oh yeah, this doesn't autocomplete. All right, so we're in the environment now. So we're going to go ahead and create a script. And remember, we are not just using the pre-trained models, but we're also going to fine-tune them, right, this time around. Very much like what we did with FastAI. Actually, the way that I think it worked is that FastAI came first as a company. Then some of the people and students from FastAI, because FastAI has a lot of like trainings, they went over to Hugging Face. And so Hugging Face then decided to do something similar to what FastAI did, but for transformer modules. And hence they created the transformers module, which I like. I think it's still, I think it's great, actually. It's pretty good. All right, so let's call this one fine-tune BERT. So it's gonna be a BERT model. And we're gonna say for single sentence classification. So what this means is that we're gonna take the original BERT, and at some point later in the semester, we'll talk about, so I've already, at this point, I've given a lecture on just the original paper, the 2017 encoder decoder with multi-head attention. Then later in the semester, I'll probably go through a few of the iterations, BERT, Roberta, and then GPT. You know, that kind of seems like a reasonable thing to do. So we'll see. All right, so I'm going to say fine-tune here. Fine-tune BERT, single cent classification.py. Okay, so we've got our script. Is there a way to make this bigger? Okay, so here, our goal will be to train a model, right? So I'm going to use the GPU. So I'm going to import torch. Import torch. So let me just Control X. And then I'm just going to run this. Okay, good. So now we can continue. So import torch. We're gonna from torch import CUDA, and this is just so that we can use the GPU. So we're gonna create an object called device, and we're gonna say that this should be CUDA if CUDA is available. So CUDA if CUDA dot is available. Okay. Else CPU. So basically, this is just a parameter that tells the script, you know, do this in the GPU or not. So that's the idea. Then let's import the transformers module. So I'm going to do from transformers import, and we're going to use one of the BERT versions. There's BERT. There's also distilled BERT, which is a simpler version of BERT, smaller, and so we're going to use that one for this example. So from transformers import, and notice that you usually import the tokenizer, and then we import the class of BERT that we want for our problem. So for this specific problem, we're trying to do classification. So we're going to import a class developed by Hugging Face that allows us to leverage BERT for classification problems. Okay, so just be aware of that. That's what we're doing. So from transformers, import, distill, BERT, And this is going to be the tokenizer. We usually need a tokenizer and then the model. I already explained in the previous lecture the difference. So tokenizer fast, right? So this tokenizer fast, I've been reading about it. It's supposed to be like an efficient implementation of the tokenizer. So it's supposed to be really fast. One thing I actually, in the document that I'll provide, the transformers document, I've actually, that document is divided into two sections. What is called the data wrangling part and then the actual modeling. So the data wrangling part is really the tokenizer. So that document has the tokenizer is implemented completely from scratch because I really wanted to understand how these work like from scratch. So you'll see in that document, you know, how that is. But anyway, so from transformers, import distill BERT tokenizer fast. And we're also going to bring in the class that will allow us to fine tune BERT for classification. So that's going to be distill BERT for sequence classification. Okay. So we want to specify which model we're going to bring from Hugging Face. So we're going to say model path. And this is going to be our model. So in this case, distill BERT based on case. Okay, so we're going to use this version of BERT. That's a pre-trained model already available. So distill BERT based on case. Now we need to initialize our two instances for the tokenizer itself and the model itself. So notice here, we're going to say tokenizer equals something and model equals something, right? So for the tokenizer, we will use this thing that we imported here. So distill BERT tokenizer fast. Okay. And then we're going to, from this object, we use the function from pre-trained model path. We're going to do the same for the model class. So we import distill BERT for sequence classification. And then we're going to say the same thing from pre-trained model path. However, for this one, there's a few other things that we need to specify because this is a class for distill BERT for us to perform sequence classification. That is, we provide inputs that are sequences, sentences, and then it should predict some class for them, right? But this is not in the original BERT. We need to add this as part of training. So we need to provide examples of sentences and their annotated labels, okay? So that's the key thing. So we need to specify what these labels look like. So a way that this is done in this class is to do ID2 label. And this would be a dictionary that specifies the mapping. So this is a binary classifier by default. So it's going to be 0 or negative. So we're going to do sentiment analysis. And then comma, 1 for positive. Like that. Okay, and that gives us our dictionary. Then we look at the next one, and then we're just going to do it in reverse so that we can do this quickly. So label to ID, it's just the inverted version. So that's going to be here. Label to ID, so we do -0, comma, positive, oops, and that's going to be 1. Okay, as you can see, that basically allows us to define the tokenizer pre-trained model and the model pre-trained also. We specify the labels that we're going to use. And then once we have that, the next step is to specify the data set. So in this case, I'm just going to use a data set from the data sets module. Let me add a new line here. So we're going to do from data sets import load underscore data set. And let me actually at this point just save it, run it, make sure that it will actually run. Right, so it says some weights of the model checkpoint at the still BERT were not initialized. This is expected. This is, and then some weights are not initialized. You should probably train this model. So we're going to do that, right? So then I have our model here. So I'm going to go back to the code. So from data sets, import load data set. Everyone with me so far? Any questions?
No question.
So remember, the goal of this is basically to do fine tuning. So now I'm going to need some data. So I'm going to use the IMDb data set available in data set. So I'm gonna need data set. I'm gonna do train, test, and validation, right? So I'm gonna do IMDb train, IMDb test, and I'm gonna do IMDb validation. Okay, so I have these three. So now we're going to call load data set, and we're going to select IMDb, comma. And then we're going to just say that from that, we just want the split called train. Remember, we're just bringing this in from this load the data sets object. Now apparently the data sets module only has train and test, but we want 3. We want train, test, and validation. So we're going to use the test split and actually divide it into 2 parts so that we can get test and validation. All right, so we're going to take that. So we're going to take load data set IMDb split, and here we have to tell it split. We're going to tell it here that we're going to use test. Okay, so in both cases we're going to use test. So in both cases, we're going to try to use test. But we're going to slice different parts of it. So I'm going to do load data set IMDb split, and then this is also test. Okay, but now from test, we're gonna slice out just parts of it. So I think there's about 12,500. There's 25,000 in one, and I think there's either in the train, there's 25,000. The test either has 12,500 or 25,000. I can't remember. So we're going to see here. First of all, from test, we're going to take all the samples until 6250 plus all the samples, should be a plus all the samples. So from 0 to 6,250, and then we're going to slice out the last 6,250. So to do that, we can use a negative number, and this just means that we start at the end. We go to the end from the end to the position 6250, but in reverse, right? So we're going to take the last 6,250, and that should total 12,000. What is that? 12,500, right? And then for the other one, for the validation, we're going to need to slice out. And we can now go, since this is the first 6,250, now here we can go from 6,250 to what? So we did so it should be if there's 25, what is 25,000 minus 6,250? Do you guys know by any chance? Could you give me that number? Nope.
Like 18,750 or something?
Well, let's be precise.
820.
How many?
820.
820 like that?
Yeah. What? Not 18, just 820.
Oh, 18,200, you mean?
You said 6,250 minus what?
I said 25,000 minus 6,250.
Shouldn't it be a 750 then?
Yeah, it's 18,750.
Yeah.
18,750, okay. So I'm just slicing, the middle part. So both of these should have 12,500 if we did this correct, right? So then I'm going to go over here. Now let's print out the dimensions. So I'm going to do print IMDb train. Oops, IMDb underscore train dot shape and print IMDb test dot shape, print IMDb val dot shape. All right, so let's run this one. Control X, Y. Okay, and as you can see, we've got the train set, which is 25,000, and then we've got the test set and the validation, which are 12,500. And notice that they have two columns, basically. right? They have 2 columns. So now let's see if we can just view this with a pandas frame. So we want to get a feel for what our data looks like, right? That's usually, you know, with these things, that's the most important part, right? So looking at our data, so let's import pandas as PD, and then let's do print, and let's do PD dot data frame. Data frame. And let's just take one of these, let's say IMDb train. All right, and let's run it. Let's see what happens. I'm trying to figure out a way to view it. All right, and there it is. So there's my data that I downloaded from the IMDb database. It's got a sentence. I rented, I am curious, you know. So these are just text examples. And notice that they have the labels associated with it. I believe the way it works is like the first half is positive, the second half is negative. Okay. So like the first 12,500 are positive examples. And then the second one are like this. That's the reason why when we did this, these splits, we did them like this. It's because, you know, the first half is negative, the second half is positive. So that's why here we grab the first 6250 and the last 6250. That way we have equal amount of positive and negative. And then here we grab them from the middle, right? So the first half of this is negative, the second half is positive. Do you guys see that?
Yep.
Make sense, guys?
Yeah.
All right, perfect. All right, so we saw, so if we run it, we see that we have our data, right? So we have a pre-trained BERT that speaks English, basically. We can think of it that way, but it doesn't speak sentiment analysis, right? That's what we want to do. So the way it works is that Hugging Face has created this object called DistillBERT for sequence classification. This one over here. And what DistillBERT for sequence classification does is that it takes the whole BERT model, but in the very last layer, it removes that layer and it puts in a new, what is called a new head. And this new head is for classification. So we already specified that it's 2. So it's like we're linking the old model to this new layer, okay? A new layer in neural network terms. The other thing that's important to understand here is that most likely all the weights in the original transformer are frozen. So what that means is that when we're doing the training, we're not updating those weights. And instead, we are only updating the last layers that were added because we have to learn those for our specific problem of positive or negative. Do you guys understand that? Or do I need to do like a diagram of it? Is that clear?
Good.
Yep, makes sense.
Makes sense. Perfect. Perfect. All right. So that's what we're doing with pre-training, right? So, you know, and the beauty of this is we can actually do it in the native PyTorch, but Hugging Face, you know, just like Fast AI did for image processing, they're doing it for transformers. So we have looked at what our data looks like, you know, just kind of like that, very nicely. Where am I? Huh. Did my connection die? I think. All right, guys, my connection. Can you guys hear me?
We can
Yeah, we
still
hear
hear you.
All right, I think my oh no, can you see it now? Let's see. Maybe it just got slow. Hopefully. So Yeah, I think it's working now. All right, hopefully it just got slow. All right, so we looked at the data. That's, to me, that's like, you know, trickiest thing, right? So it's complicated. Then after that, we have our data, right? We have our data like this. But as we have explained in the transformer lectures, we have to tokenize this, right? We have to create the masks. We have to tokenize it so that we can actually use it in our transformer module. Okay, so that's the next step. So we're going to need to use the tokenizer. So I'm going to go ahead here, and now we're going to call the tokenizer. So I'm going to use the mapping function and lambdas. They're actually not so complex to understand. So let's create an object encoder train, and we're going to call IMDb train dot map. Okay, so IMDb train dot map, and here we call something called a lambda. This is basically like a function for transformation. So everything is E, like an event. And then we apply. So we're going to grab each object, right, in the frame, each row, and basically because of the way they are, we can reference them by name. So I can reference E text, right? So I reference E text, and to this object, I'm going to apply the tokenizer, which is the thing that we have up here. Tokenizer, this object right here, right? And so we're going to apply it to the text. So this then is, we call tokenizer. And E is the input, E text. But the tokenizer also needs a few parameters. If you remember now, since I'm doing this lambda, this, and then I'm going to move this down like that. Okay, so I kind of have that there. And now I'm applying a lambda. So I'm applying to E text, the tokenizer. But the tokenizer has some special fields. So now I can close the tokenizer, and the fields are padding. So remember, padding just means, let's say that the number of objects is 40, but the text is less than 40. So then we would pad the rest, right? That doesn't get filled in. So padding is going to be set to true. And then we do truncation. We're going to set this parameter also to true. And it's the same idea. So if the sentence is longer than 40 tokens, we just truncate it and lose some information. Okay, and that is the that's the tokenizer, basically. Now, the other thing that we can do here in the mapping is we're going to set for this object that it is batched. So we're going to send the information in batches. Batched. So we're going to set that to true. And also, and there should be a comma. And finally, we're going to set the batch size to 1,000. Okay, so batches of 1,000. So now maybe we can even move this down. And move this parentheses to the end. Okay, so let me run this just to make sure that there are no errors. So notice that this text is what I'm referring, right? So I grab every row and I can refer to it by the label here. This is how it is in the data set. So text, and I'm grabbing the text and I'm running the tokenizer through it. So here it's running the tokenizer. All right, so that should have tokenized all of the sentences for the IMDb train. So now I can just copy this and do it for the other ones. They all need to be tokenized. Why is that not working? It's not letting me copy. All right, so let's just type it up. Encoder test is going to be the same thing. So IMDb underscore test dot map lambda e. And again, we called a tokenizer. The tokenizer e text padding equal true, truncation also true, close the parentheses. And then we're going to say that this is batched, true, and batch size equal 1000 as well. And then finally, the other one, encoder validation, IMDb val.map lambda, call the tokenizer again, tokenizer. We tokenized the text, so e text. We specify that we want to use padding equal true and truncation true. And then we're just going to say batched equal true. And finally, batch size equal 1000. Okay, so we've got basically our three data sets. They are now converted by the tokenizer. So the data is now in the format that the transformer expects it. So if we want to test this, we're going to use the same pandas, but now we're going to print out the data after running the tokenizer. Okay, so let's do PD data frame encoder, so encoded train. Encoded train. Okay, so we're going to try this one. All right, so let's run it. So Control X, Y. Clear here. Oops, there's an error. Missing a comma. So there it goes. So we have the original text. Should be tokenizing everything now. And now we have after the tokenization. Do you guys see? So this is the original one, right? It's got the original sentence and the label. After running the tokenizer, notice what happened. It takes the original text, the tokenizer, there's the label still, but now notice we've got these two new things. We've got the input IDs and we've got the attention masks. Do you guys see that? So remember, the attention masks just indicate really quickly when we do matrix multiplications, what are tokens versus padding, for instance. And then here, these are the words converted. Notice that they all start with 101 because if you remember, you always add a symbol to represent the start of the sentence. So 101 is the start of the sentence. So like, you know, S or start of sentence, whatever the mask is. So or whatever, sorry, whatever that symbol is. But it's always represented. And then after that, they are all the letters. So for instance, I starts here, and then there's another I here. So I here is 1045, and then down here is also 1045. Do you guys see that? So we have a way, we have basically converted into IDs, and we've also converted, we also have the attention masks. Notice that the dimensions are now, instead of 25,000 by 2, it's 25,000 by 4, because we've added the input IDs, we added the attention masks. Questions so far? Nope. All right, now that we have this, in the interest of time, because I don't want to run out of time here, I'm going to copy from my GitHub the next part, which is the arguments of the transformer. So the transformer actually has a lot of details, you know, a lot of parameters. So I'm going to go ahead and just copy the code. Okay, guys? Because I'm seeing the clock. So copy this. All right, so you should be seeing my screen here. So we're going to open up. Hopefully I can copy this. I'm going to scroll down here. And then I'm just going to add down here some comments. So I'm going to do 1, 2, 3, 1, 2, 3. And then in here, I want to paste the code that I just copied. There it is. You guys should be seeing that. All right, and I'm going to save it before I lose it. All right, great. So now that is, let me just run it to make sure there are no errors there.
Well, I do have one quick question.
Go ahead, sir.
So when we're doing this from the start ourselves, there's going to be a lot of downloads, right?
Okay, what do you mean a lot of downloads?
Well, because I followed along and I still have downloads occurring.
I'll have downloads.
Yeah, from probably the training sets and test sets. And
is your bar green or blue?
the way this is supposed to work is that you only download something once and then it gets cached into your system. Like the Transformers library has a cache folder somewhere. You can actually see it here, cache. And so you only download that.
I was just going to say, so since I've never ran this before, everything is being downloaded.
Yeah, that's true. So like my computer is pretty fast, but I actually ran this before, right? So I wrote this code and I loaded it to GitHub. And this is the second time I'm doing this in another folder, but because it's getting it from cache, it might be much faster than yours. That's a possibility.
Yeah, that's what I think.
I think it does the tokenizing require like some sort of processing? Because I had like the green bar, which I usually have when I download stuff, and then I have a blue bar that was like, it goes like examples per second or something, and then there's 25,000 of those. So I'm assuming it's tokenizing the text.
Yeah. Yeah, I mean, it is tokenizing, right? So it's taking this and producing these, but it's a pre-trained model, so it should not take that long, I would think. The tokenizer
just finished.
Yeah. So yeah, it might be that mine is a combination of being fast, but also I've done it before.
All right, just wanted to check. Thanks.
No problem. All right, so we have like 20 minutes, I think. We can wrap it up because I have, and then I want to give you the homework. So, which I think you'll find the homework fun. So this is where we are, right? So I printed out the tokenized version. So now here, ATF. So now the next step is, just like when FastAI, if you guys remember FastAI, we had a trainer object, right? And guess what? We have a trainer object here. So you can see from transformers, import two things. We import the training arguments and we import the trainer. So the training arguments are basically all the parameters for the transformer. So let's take a look at that first. I'm going to add a comment here. Okay. And so you can see here the training arguments, we're going to use training arguments, this class. We instantiate it here by saying training arguments. And then now I have a few parameters. So what are they? The output directory where the model predictions and checkpoints will be written. Remember that this is a lot of this is sharing models. That's kind of the philosophy of Hugging Face. So they're very big on saving your models and they want you to upload them to the hub, right? So that's one thing that you can expect. So there's going to be a folder, output directory, my IMDb model. Then you're going to do both train and evaluation when you're doing the learning. You specify the number of epochs, which defaults to 3. So if you notice, whenever we're training from scratch, we always do a lot of epochs. But if you remember from FastAI, fine-tuning was only very few epochs. Do you guys remember that? So it's almost like we learn really fast, right? Because we're leveraging, we don't have to learn everything, just the specifics of our model. Got it? Then the per device batch size here. I think I reduced these to 16, but as long as your cache is available, you can probably put in like 64 here on both, and it should be pretty fast, I think. But if it's breaking, make sure you reduce these sizes to something more manageable. Like I remember on my laptop, for instance, I had to make these pretty small. Number of steps for a linear warm-up. So this is just, a warm-up steps to kind of test out the data. Decay, we've talked about this, I think. This is when you drop some weights in the model. Login strategy, right? So how you're going to log, basically. Information about TensorBoard. So that's something I'm not using right now. Login directories. It's got a lot of little details, like where you would log things. login steps. So every 50 steps, it creates a log. The evaluation strategy. So every 50 steps. This has to do with the size, floating point 16. So if you're using CUDA, you can specify 16 or some other value, and it's supposed to make it a little bit faster. Saving strategy every epoch, and then I commented out this last one. So that's the training arguments that you can set up, okay, for your model. Then after that, we still haven't called trainer, but before we call trainer, we also need to specify some metrics, right? Now, the metrics that we use when we use classification, if you remember, are precision, recall, F measure, and so on, right? The things that we're used to. So from sklearn metrics over here, we just call accuracy and F1 score. So this you guys are familiar with. Just keep in mind that the transformer module can give you both the predicted and the true labels in one single object. So it's going to be pred. And then here, if we want to reference the actual predicted and true, we go to pred and dot label IDs. So this is the real data, right? The real data that we have, label ID. So if I do Control X, Y, it's these, right? The label IDs, those are the real. And then the predictions are going to be pred predictions argmax 1. So what this means is that it gives you a tensor, right, of predictions. You know, so there's two classes, so it's going to give you a tensor of two things. And you just select from the last dimension the index of the highest value. So that's going to give you the actual predicted label. Okay, so remember, this is going to be two neurons, if you will, in the last layer. That's what the -1 is for, the last dimension. And out of the two, select the max. Argmax returns not the value, but the index of the highest value. So that gives you labels and preds. And then given that this is just pretty standard how we've always done it, we give labels and preds to F1 score, we give labels and preds to accuracy, and then we just return this as a dictionary, basically. All right, and those are your compute matrix to evaluate. And then finally here, we are ready then, just like in FastAI, to call up our trainer. And so the trainer, we instantiate the class, and now the pre-trained model that will be fine-tuned, that's just model, right? So the model that we brought in up here, right? This one, model, the still BERT. So we plug that one in, okay? Then the training arguments, that's args. Then we provide the data sets. Notice that this is important. This is the thing that, to me, I kind of want it like the trained data to be one thing and the labels another thing. But in the trainer, it's not like that, right? In the trainer, you know, it basically expects you to bundle it. So we just provide the trained data set and the eval data set which are gonna be encoder train and encoder val. But keep in mind that though the labels and the data are there. So encoder train is this one, right? So remember, this is the whole thing we're giving it, but it's gonna use basically this label, and it's gonna use the input IDs and the attention mask, okay? So this is important because whenever you're doing, let's say that you have your own data, for instance, you're gonna have to be consistent in the way that you create your data set, all right? To fit like this. So now I have here train data set, eval data set, and then compute matrix that we just defined. And then now we just call trainer and we say train, basically. And then that's going to give us results. Okay, so that's going to give us our results. So if we run this, let's do that. You should be seeing the model running. And there it is, it's going. So it's 28 to 30%. And this means that it is currently fine tuning. Okay, so we are now at this stage fine tuning the model. So we're fine tuning the model. Okay, you can see it's starting to output some results, evaluation, loss, and the accuracy. It's doing the epochs, basically. Any questions, guys, while it's doing this? So it's fine tuning. And it's probably very slow, I think, because I made my batch sizes 16. I think if I had made them 64, it would be a little bit faster. So I may have to, where are we on the iterations? Yeah, I think it's going pretty slow. So let me kill this. And I'm gonna do NVIDIA SME here. SMI. Huh. I thought this was the command. You guys remember this command?
Do you need a dash instead of an underscore?
Yeah, there we go. Thank you. So Python, I'm going to kill that process. Kill -9 27948. Yeah. All right. So thanks, Jason. And then, okay. So I'm going to increase. I'm going to increase in the configuration file this to 64. You got to clear the cache in the GPU, but then this should work, at least for my GPU. So it goes a little bit faster. And then let's just try to finish up the code because we can't run this several times. So now here, we've trained the model, hopefully. So now we want to save it, save the model, saving the best fine-tuned model and Tokenizer. So notice we just specify the path. And then we're going to say trainer and Tokenizer, save model, and save pre-trained Tokenizer. Right, so we save them. And now we create a little function for predicting. So our trainer is trained. So now we want to do a prediction. So notice here, I'm going to do a function get prediction. So I give it some text. So notice here, right? I'm gonna say use the model with the device GPU. Here's the text. I didn't like the movie since it bored me. So that should be a negative, hopefully. And then what we do is we call a function get prediction with text. This returns two values, right? It returns two values, the loss and the prediction. So we select the second one. So not 0, but 1. And then we select the item, and then we print it out. So here we go to this function. This, takes the text. We have to, again, tokenize it so that we have IDs and masks. So text, padding true, truncation. The max length is 250, and return tensors PyTorch. We have to tie this to the device GPU. That gives us the inputs. And then now we're going to run this in the model itself. Notice that in the model, we give it two things. The input IDs, which is the text converted to IDs. And then we also give it the attention masks, right, that are created by the tokenizer. We tell it that we want all of this to run on the GPU. That's what this is, what this thing is about. And then finally, outputs gives us some values here. Which are the probabilities. We run softmax through it so that we map them from 0 to 1 as a probability. And then this probs here, we do the argmax. Okay, and that's where this should give us the ID, either 0 or 1 for negative or positive. But it also gives us the original probability. So that's why here we do this one. Now this code could be a little bit different. I mean, this is up to you guys how you do it, but just keep in mind, these are the outputs of the model. We run softmax on it so that they're like probabilities now, 0 to 1. And then we predict the class. So if we run this, it should give us either 0 or 1. 0 is negative as we've defined it. So then it should return 0 here. So I'm going to do Control X, Y, clear. Run it. All right, so let's let it, hopefully this will be faster. Oh, yeah, out of memory. You see I got this error. Even though I did the NVIDIA SMI, I guess I don't have enough memory. So I'm gonna have, when you get this error, I always have to reduce the size of those things, fortunately. Let me do 32, maybe that'll. Let's see if this works. Nope, doesn't like it. Yeah, so CUDA out of memory. All right, I'm gonna have to go back. That 16 had worked for me. before. If you guys know how to solve this, you'd do me a huge favor because it's one of the things I always have trouble with.
I don't think you can solve that without getting a GPU with more RAM or memory.
Power. Yeah. So that's what I mean. Just give me a GPU with more power.
Yeah, it's kind of expensive.
All right. So yeah, let's see if this time it works. All right, seems to be training. We're running out of time, unfortunately. We only have, so I'll leave it running, and if it comes to the end, it should print 0. Okay. And so that would be the whole process of fine-tuning a pre-trained model for a specific task, such as sentiment analysis, classification between two classes. Did you guys understand this, or are there any questions?
No questions.
No questions. All right. So homework. In the last 3 minutes, here is the homework. Let's let this run, but let's let me show you the homework. All right, so I'm going to share this. All right, so you're here, right? So go to this link, GitHub, Mastering Transformers. So get that link there, okay? And go to chapter 4. So chapter 4 is an it talks about autoregressive models. So in particular, it talks about this one, autoregressive language model training. So open this Jupyter notebook. And this Jupyter notebook, if you notice here, trains GPT, right? So this is, it's not like BERT, this is the other, not there's the encoder-based transformers, and then there's the autoregressive transformers. So this is GPT, not GPT-3, because you have to get an API for that one, but GPT-2 you can do. So basically what I want you to do is, this is written for TensorFlow. You see that? This is written for TensorFlow. I want you to basically take this code, reverse engineer it into PyTorch. What it's supposed to do is, it's supposed to do natural language generation, basically. So you give it a sentence like, Watson was very good. And then from there, it's going to start telling you a story. You guys see that? You can use whatever text you want, but I think it would be a fun thing. So what I want you to do is create a GPT transformer. You can use this as reference. As I said, this is written in TensorFlow. Convert it to PyTorch, and then run it to generate text, stories. And you can use the Gutenberg books or whatever you want to do this task. I think doing this would be very good because translating from TensorFlow to PyTorch will really allow you to get a really good sense of how things work. Do you guys understand what I'm saying, guys? The homework?
Yep.
Yeah.
I mean, the code is here. Like literally, this is the code, but it's only for TensorFlow, right? So you can run it in TensorFlow and get a feel for that, and then translate it to pure PyTorch And then remember, the task at the end of the day is to generate stories. So like if you trained it with, you know, let's say Star Wars, right? It would start telling you stories that are Star Wars related. So we talk about planets, the Empire, you know, things like that. What usually happens with this is that the semantics look very accurate, but it's like the story is like completely fake, right? It just makes up stuff. But it should be a fun one, I think, a fun assignment, because you want to generate. This is the so-called fake news that they were so worried about. The reason why in the last election, for instance, the reason why OpenAI did not release GPT-3 during the last election is that it was so good that they were afraid that it was going to be used to just generate like a lot of fake news. And so, I kind of want you to play with that. Keep in mind, this is GPT-2, not GPT-3, but still, that's the homework assignment. So take this one from this site, convert it to pure PyTorch, and then just model it like this one, but in PyTorch, and generate some stories. And then hopefully pick some books different from Emma, right? So pick something that is of interest to you. And that's it. So that's the homework. Now let's see if the model finished. Still going. All right, so we're at, okay, go ahead.
Is that on your website?
It's not on my website. So you can look at the video for reference, but the homework is, yeah, it's basically this.
I pasted the link in chat.
Yeah, thanks, Kyle.
Yep.
Yeah, so just go to this one and convert it to PyTorch, basically. As I said, it's a complete piece of code, but by translating it to PyTorch, which is what we've been using all semester, it should be good, right? To understand the details. It'll get your hands dirty, and so it should be good. Any questions?
Just one question. When is the due date?
Oh, this one, well, we got spring break, right? So that's why I kind of rushed. I wanted to give you something to do during the spring break. Let's just work on it, and then we will, when we meet again, we'll see where we are. How about that?
Sounds good.
Right.
Yeah, these homework assignments are not trivial, right? So none of them are trivial necessarily. So I want to give you enough time, but I think there's a lot to be gained from this exercise. All right, so hopefully that this has been useful. Also, you can check my GitHub where, the one where it says like fine tuning. I have a lot of scripts there beyond the one that we did today in class, but I don't have this one. See, that's the thing. I don't have GPT in there. And so this gives you an opportunity to do one from scratch. Okay?
Got it.
Perfect. All right. So if there are no questions, I'll keep monitoring this model. Let it finish. At the end, it should predict 0, negative. If it does that, then it works. All right. And so, yeah, so we'll stop here for today and have a good break.
Thank you.